your conclusion will be that if you have a function that you want to integrate over a union, then the integral over that union should be the same as the sum of the integrals over the individual pieces. But you should subtract off the integral over the intersection, which is the same as adding it to the other side. Let's try to prove that. And in fact, the proof will follow kind of by thinking about why this walks on the nose. Because if you think about trying to, the interval from A to B is a set, the interval from B to C is a set. What's the intersection between those two sets? It's just B, right? Which, if you integrate over a set containing one thing, you get 0. So the thing you double count as 0 anyway. We'll first prove this claim in that same context, well, but a higher dimensional version, where the thing that we double count has to be 0. So let's set it up. Let's let x and y be figures. Let's let f from x union y to r be bounded. We've proven already that the intersection and union are figures, right? We even said how to compute the volumes of them. So these things are figures. So we can talk about integrals of them. As has been my habit, I'm only going to go through the proof for the lower integral. And what I was trying to suggest with this illusion is, well, let's prove the theorem first when the bit that we double count should be 0. So let's prove it in the context that the volume of the intersection is 0. Let's assume the volume of x intersect y is 0. If you integrate over a thing that has no volume, what should the integral be? Probably 0, right? And in fact, that is a homework problem. It's not a hard homework problem. You show that all of the, no matter how you subdivide it, you're subdividing it up into pieces that have no volume. So all of the sums are 0. We'll remove that assumption later by considering different decompositions of x union y. So let's do it. Let's assume that. And now I'll consider any subdivision of x union y. I'll set delta x to be everything of the form j intersected x, where j is in delta. Delta y will be the same thing, but I'll intersect with y. So, pictorially, if there's a decomposition of this set into pieces, then the pieces that I would be using for y take all of the pieces of the decomposition, intersect with each individual. Is that still a subdivision of y? Is the one where I intersect with x still a subdivision of x? Should be. Let's explain why. What do you need to check if you want a thing to be a subdivision? What's the definition of a subdivision?
Here, the union makes the original set, and the volume of the intersection of each version is 0.
Yep. Well, I guess there's also the hidden one that it has to be a finite collection, which it still is. Do you want to talk through why this satisfies each of those conditions, or do you think all of those seem straightforward? Should I talk? Okay, let's go through them one at a time. First, let's show that x is, so the first thing that is needed is x is equal to the union of all j in delta x of j. One containment is like obvious, right? Oh. Because each of these things in delta x is already an intersection with x. That's always a dangerous one, obvious, but I thought that it is if you write down just a little bit. Let's go the other way. Let's let x be in x. I now need to exhibit an element of delta x containing that x. But let's start with this. Is there an element of delta which contains that x? Because delta is a subdivision. As delta is a subdivision, there exists, I don't know, I'll call it I because j looks like it already has a job above, in delta, such that x is in I. But now check it out. Delta x is just intersection of things in delta with x. I have x in I and x in x. So is x in the intersection? Yeah, that's all it needs to be in the intersection. Then x is in I intersect x, which is an element of delta x. So x is in the union over all j in delta x of j. So that completes the proof that of the first condition to be a subdivision. Well, no, that's the second condition. The first condition is they all have to be figures. But that's like super obvious, right? Is x a figure? Is each element of delta a figure? Intersection of two figures is a figure. Yeah, I guess out of one, that was 2, this is 1. Let's consider any j intersect x in delta x. So j is in delta. As j and x are figures, so is j intersect x. Nice. And I guess the third condition is volumes of intersections need to be 0. And this time I think I have given myself enough space for the individual items. So let's take any, well, what do two things in delta x look like? They look like j intersect x and I intersect x in delta x with j and I in delta. I now need to compute the volume. Then, let's see, let's try to compute the volume of j intersect x intersect I intersect x. Why should that have volume 0?
That's the same as j intersect I intersect x. J intersect I is volume 0.
Yeah. And is that a subset of j intersect I?
Yeah.
Yeah, intersections makes that smaller. So that's less than or equal to the volume of j intersect I, which is equal to 0, as, oh, these two things had better not be equal, as delta is a subdivision. Cool. Do you think to prove that delta y of the subdivision is probably the same? Yeah, like it's practically verbatim the same. All right, so now let's go back to the picture, which is a bad picture. There's an easier subdivision and an easier union to draw. So we've broken it up into two pieces. We have the things in delta x. We have things in delta y. I claim that now that delta x union delta y is a subdivision of x union y. So one thing that's a little bit suspicious here, can you see a thing in delta x and a thing in delta y which have some intersection in common? Yeah, I see that little tiny piece of green, that's a thing in delta x that is completely contained in a thing in delta y. Oh, but this picture is just dishonest, isn't it? Because what did I assume about the volume of the intersection of x and y?
It was 0.
0. This is a subset of the intersection of x and y, so what's its volume? 0. So that's fine, right? Because we assumed we're allowed to have elements of a subdivision are allowed to intersect each other as long as they do so in 0 volume. So that's like a sketch of why delta x union delta y should be a refinement of delta. People want to go through the details of that? Okay, then let's do it. So first, let's check that it's a subdivision. And some of this, maybe I'll wave hands at. Let's see, is it a finite collection of sets? A union of two finite sets still finite. Is each element of that collection a figure? Yeah, because we checked that delta x and delta y are subdivisions, so everything in delta x is a figure, everything in delta y is a figure. We need x union y to be contained in the union. Well, anything in x union y is either in x or in y. If it's in x, it must be in one of the delta x's, one of the things in delta x. If it's in y, it must be in one of the things in delta y. So either way, it's in the union of all of the things in delta x union delta y. And then the final thing is volumes. And let's actually write a few words about that. So let's consider any A not equal to B in delta x union delta y. Let's show that the intersection between A and B has no volume. So if I have two things in a union, it seems like there can be up to 4 cases, right? A could be in delta x or it could be in delta y. B could be in delta x or it could be in delta y. But the case that A is in delta x, B is in delta y, that's the same as the case that B is in delta x, A is in delta y. And the case that they're both in the same thing is probably going to be the same proof because there's nothing special about x that's not true about y. So let's just deal with that case first. So let's suppose A and B are both in delta x for now. We already know that delta x is a figure. That delta x is a subdivision. So what do I know about the intersection of A and B right now? Volume is 0. Then a volume of A intersect B equals 0, as delta x is a subdivision. Do you think the same proof should walk if A and B are both in delta y? So the last case we need to worry about is if one of them is in delta x and the other one's in delta y. So now let's let A be an element of delta x, B be an element of delta y. And see, these are one of them is a subdivision of x, the other is a subdivision of y. So, in particular, A is a subset of x, and B is a subset of y. And now let's try to compute the volume. So pictorially, this is like this case, where there's the A, there's the B. So by looking at this picture, I don't know what this one. There's B, there's A, no, no. Well, neat. So A intersect B, what is that contained in?
X intersect y.
X intersect y. So by monotonicity of volumes, volume of A intersect B is less than or equal to volume of X intersect y, which is by assumption what?
0.
Are volumes allowed to be negative? Nah. So the volume of and the intersection of any two things is in fact 0. Do you think that this step would have walked if I didn't have the assumption that the intersection of x and y has no volume? And I mean, you can visually see why. In this actual picture, there is a piece which has positive area.
What's the, like, greater than 0 doing
This one?
there? Yeah.
Oh, volume is all. The volume needs to be equal to 0.
Yeah.
And volume is always bigger than or equal to 0, right? So that's why it's a subdivision. And now let's think about why it's a refinement of delta. So what does it mean to be a refinement of delta?
For everything in x union y, or delta x union delta y, there is something in delta that contains that. And the union over all things in delta x union delta y is equal to delta.
Yeah. Well, I've already checked the pos one now because that's just what needs to be a subdivision. Union of all the things in the subdivision needs to be x. So let's check that. So let's check for that it's a refinement. So let's let, I don't know, A be an element of delta x union delta y. Well, then it's either going to be in delta x or delta y. So without loss of generality, let's say it's in delta x. But what does it mean to be in delta x? What's the definition of delta x? Well, it's like there. It's the intersection of a thing in delta with x. So let's write that down. So there exists, I don't know, I in delta, such that A is equal to I intersect x. Oh wait, did I just accidentally produce an element of delta that contains A? Yeah, I. Since A is a subset of I is an element of delta, delta x union delta y will affines delta. Cool. Does that seem pretty okay? All right, so this will all come together soon. But let's justify one other thing. So the delta x union delta y, that now gives us a thing that should be able to approximate the integral over x union y. It's a refinement of x union y. Delta x gives us something that we can use to approximate the integral of f over x. Delta y gives us something we can use to approximate the integral of f over y. Well, that basically is going to give us what we want. An approximation for the integral of f over x plus an integral plus an approximation for the integral of f over y is the same as an approximation of the integral of f over x union y. So that would be really good if we could prove that. Let's try to prove that. And in fact, I just thought that this will be like really easy to prove. What's the definition of? Let's just start by expanding the left-hand side. So that's the s minus of f delta x plus s minus of f delta y. Gesundheit. What's the definition of s minus?
The summation of the volumes of every j in delta x times the infimum of f over j.
Yeah. And then I need to add to that the same thing, but with delta y. Because I also want that one. Oh, wait, but did I just like count up all of the j's in delta x and all of the j's in delta y? So that's the same as the sum over all j's in delta x union delta y, volume of j times m of f comma j, except I've double counted some of them, right? I've double counted the ones in the intersection. And I'll write that, but you already know why that's fine. Oh, that should be minus. So if j is in delta x intersect delta y, then what's the volume of j?
0.
So I'm adding up a bunch of zeros. So I see exactly s minus of f comma delta x union delta y minus 0. Which is exactly what we need. Everyone feel pretty okay? And now you should really feel like the proof is almost completely done. It's just a matter of doing some bookkeeping, right? I can get that to be as close as I want to the integral of f over x. That can be as close as I want to the integral of f over y. That can be as close as I want to the integral of f over x union y. So, I mean, like there's some bookkeeping, but it won't be bad. So let's compare s minus of f comma delta with all of these things. What did we prove about x union y? delta x union delta y? About comparing that to delta?
It's a refinement?
It's a refinement. And these are supposed to be lower bounds, right? So the refinement should give us a better lower bound. Should a better lower bound be bigger or smaller?
Bigger.
Bigger. And that's what proposition 2 says. You can flip back and double check that that's what proposition 2 says. But hopefully that's what proposition 2 says if I'm referencing what I think I'm referencing. Well, now I don't have confidence. Yeah, proposition 2. S minus of f delta is less than or equal to s minus of f comma a refinement. Well, you couldn't see that. Anyway. S minus of f comma delta x union delta y. But we've just shown that that's the same as s minus of f comma delta x plus s minus of f comma delta y. And I claim that that is less than or equal to the lower integral of f over x plus the lower integral of f over y. And that makes sense, right? These are supposed to be like the best lower bounds on the integral. So they should be the greatest lower bounds. In fact, that's their definition, right? They are the goals of all of the s minuses. Oh, cool. Did we just explicitly show that this thing is an upper bound on all of the lower Darboux sums for f over x union y? Well, but the lower integral of f over x union y is, by definition, the greatest lower bound. Nope, the least upper bound. I think I kept on saying uppers when I meant lowers. So this is an upper bound on all of the Darboux sums over the union. The Darboux integral is the least upper bound. So we automatically get that inequality. And then let's think about estimates, right? I can find some subdivisions delta x and delta y so that, well, for any epsilon bigger than 0, I can find some subdivisions so that that happens. So let's add these together. So that means that the integral of f minus epsilon over 2 plus the integral over y minus epsilon over 2 is less than or equal to s minus of f delta x plus s minus of f delta y. And I'll put an extra equal sign there. What did I show that the sum of those two things is equal to? In equation 4 on the previous page?
S minus f delta x union delta y.
Yeah. Oh, hey, but that's like less than or equal to the integral, isn't it? Because the lower integral is supposed to be the greatest lower, nope, the least upper bound. There we go. Take an arbitrarily small epsilon. And oh, yeah. As soon as we get an inequality, so that epsilon was universally quantified, right? And the stuff on the left-hand side, well, that doesn't depend on epsilon, that doesn't depend on epsilon, that doesn't depend on epsilon, so I can apply that result from homework 1 of analysis 1. Which, right, I mean, when I assigned it, I said this might seem obscure, but it's going to be used constantly. To conclude that the integral of x of f dv plus the integral of y of f dv less than or equal to the integral of f over x union y dv. Have we successfully proven that the two integrals are the same? So what do you think? Is what we've done sufficient to conclude that the theorem is true?
This is only if the intersection is 0, right?
Yep. This is true only under the assumption that the volume of x intersect y is 0. Oh, well, so let's deal with the case that it's not. And the proof will actually be, well, from here it'll be like just rearrange. I'm not going to take any more subdivisions. I'm just going to appeal to what's already been proven. So, let's see. No more subdivisions. There's x. There's y. From this picture, can I decompose x union y into two disjoint pieces? How about like this one and this one? Do those two sets, or well, let's see. What do we need? We need both of those to be figures. But we've proven that the difference between two sets is still a figure. What's the volume of their intersection? 0, because it's empty. So we can apply the result we've already proven.
So for the after line we have, since this true paragraph's not greater than 0, we include that. I thought we were trying to prove equality, not just less than or equal.
Well, it's at the top of the screen. Okay, don't hide that.
Ah, okay, gotcha.
Yes, we've proven both inequalities.
Thank you.
There.
Gotcha.
Right, so like an analyst should, when there's an inequality you want to prove it's too hard, just prove two inequalities. Nice. So let's break x union y up into two pieces. Namely, x union y is the same as x union y minus x. What is x union y minus x? No, intersect. Sorry, you answered the question that I actually asked instead of the question that I meant.
Oh, 0.
Yeah. Empty. Well, and I guess what really matters is as a consequence of that. That means that the volume of x intersect y minus x is 0. So that means that the lower integral of f over x union y, I can decompose it using this idea as the lower integral of f over x plus the lower integral over y minus x f dv. All right, so I mean, like, that's something, but the theorem that I want to prove doesn't involve a set difference. It involves intersections and unions. So let's now look at just y. Do you see in this picture a decomposition of y into two pieces, which are disjoint? That piece and that piece. Let's use that. And my goal will eventually be to solve for this ingredient. Y is equal to the union between x intersect y and y minus x. Are those two pieces disjoint? So in particular, they have no volume. The intersection has no volume. So the integral over y is the integral over this union, because this is y. That is the integral of over y intersect x f dv plus the integral over y minus x of f dv. Oh, nice. So I see an integral over y. I'm okay with there being, an integral over y in my final result. I see an integral over y intersect x. I'm okay with that being in my final result. So let's just solve that for y, the integral over y minus x. The integral over y minus x of f is therefore the integral of f over y plus the integral of f over y intersect x.
Isn't it minus?
Yeah.
Well, no, this is the minus. Oh, this minus, yeah. That should be a minus, not the set minus, but like number minus. So now let's just put these two things together. So that means that the integral of f dv is the integral over x of f dv. And then I needed to add the integral over y minus x. But I have now a formula for the integral of over y minus x plus the integral of f over y minus the integral of f over y intersect x dv dv. Is that exactly what I wanted to prove? Yeah, I guess there's a shortcut that like the minus is on the other side, but who cares? Nice. So that completes that note packet, and hopefully that proof felt reasonably concrete as far as these things go. The next goal that I want to hit is the so-called Fubini's theorem, which says that you can integrate a rectangular region by integrating it over like two variables, one at a time. But before I do that, I'm going to need just a little bit of topological properties that figures satisfy. So I won't be able to get too far into this document. But let's talk a bit about some light topology. So, two of you took topology. So you'll be maybe dissatisfied with how loose I will be with the topology. So I claim that the fundamental things you want to study in topology are the concept of interiors and closures. That seems not totally dishonest, right? Let's write down the definitions, at least in Rn, of what interior and closure means. Let's let X be a subset of Rn, any subset, and P be a point in Rn. P is interior to X if there exists a positive number delta such that the ball centered at P of radius delta is contained in X. And maybe I should recall notation. B of P comma delta is the set of all X in Rn such that the distance from P to X is less than delta. Right, that seems like a good definition for a ball. I say that P is in the closure of X if for every positive number delta, the ball centered at P of a radius delta has a point in common with X. So let's draw a picture of just what this means pictorially. So if I have some set X in, I guess, R2, let's see. Let's draw that point right there. I can find a little positive delta so that the ball centered at that point of radius delta is completely contained in X. So that's an interior point. Let's now try to, so let's think about it also. Is that also a point in the closure? If I draw any little ball centered at that point, it contains some stuff in X. In fact, it contains P. Here's another example of a point on the closure. How about that point? So if I draw a little ball centered at that point, yeah, I see lots of things really close to that point in the set X. So no matter how small a circle I draw around that point, I see stuff in X in that circle. A point is a boundary point if it is simultaneously a closure point and not an interior point. So there's a boundary point. Yeah. So let's make up some notation. So I'm going to refer to interiors an awful lot, especially if, like, I claim that interior is the fundamental thing you want to study in topology. And I'll refer to closure an awful lot. The interior of a set I'll denote either by int of X, or as X would put an open circle on top of it. Which, I mean, kind of makes sense, right? Like, I want to exclude everything on the edge, so like you would draw a dashed line around it. The closure of X is denoted by either col of X or as X bar. And there's no ambiguity there because, well, I'm not a complex analyst, there will be no complex conjugates. The boundary of X, I'll denote with partial, is given by the closure minus the interior. Everyone feel pretty good about just those definitions? So with those definitions in mind, let's just state the main theorems and then we'll go from there. So the main theorems today, the first is theorem 5, which says that if you have any set X, v minus of X, so remember that's like the supremum of the sum of all interior rectangles is the same as v minus of the interior of X. So I can throw away points that aren't in the interior and I don't change the inner volume. If I take the closure, then I don't change the upper volume. As a consequence of this theorem, if I take any set, take its outer volume and inner volume, and take the difference, that will return precisely the outer volume of the boundary of the set. Happy enough? Oh, cool. But what is a figure? What's the definition of a figure? Outer volume is the same as inner volume, right? The best lower bound I can get on the volume is the same as the best upper bound I can get on the volume, so I know what the volume is. When they're different, I can't say what the volume is, so I just don't study them. But this is a good reformulation. If you have an actual honest-to-God figure, then that difference is 0, right? So if you have a figure, the boundary has no volume. On the other hand, if the boundary has no volume, does it follow that it's a figure? Yeah. There's another definition of figures. A figure is a subset of Rn whose boundary has no volume. That seems reasonable, right? Like if you picture a set in Rn, the set you're picturing, if you could draw a picture of it, has some like boundary that's like a codimension, that's one dimension lower than Rn, so it's got no volume, right? Unless you picture the set that you should if you want to counter example, and you picture like Q cross Q, then every point is in the boundary of that set. Nice. So, those are the goals of this document. Let's start with something light. Let's compute some interiors and some closures. Let's actually do something even lighter than that. So here it's like, this is a proposition whose proof is the paragraph above. So if you have a point in the interior of X, then there should exist a delta bigger than 0 so that the ball of radius delta centered at that point is totally contained in X. Oh, but then check it out. Then X is an element of this ball, because it's the center of the ball, is a subset of X, because it's interior. Oh wait, does that mean little x is in the set big X? Does that mean that the interior is always a subset? Which seems reasonable, right? It kind of has to be. It's a subset of. On the other hand, if you take a point in X, does it seem like that point in X should still be in the closure? Yeah, and let's even like justify why. So if you have a point that's in X and you want it to be in the closure, you need to show that for every ball centered at that point, there's a point in the ball that is also in X. And, well, if little x is already in the set big X, what point are you thinking of?
X.
The point you started with. If X is in X, then no matter how small a delta you choose, then X is in the ball centered at X of radius delta because it's distance 0 from itself. And it's also in X, so it's in the intersection. So that intersection is non-empty. So x is always contained in its closure. And this might seem like, so let's prove this also. This is actually going to be a lemma that will wind up being used a fair amount, which is why I state it as a lemma, even though it looks pretty obvious. So let's let R be a rectangle, and Q be another rectangle. And let's suppose that for each of the coordinates of those rectangles, AI is less than CI and DI is less than BI. Then I claim that Q is contained in the interior to R. And let's draw a picture. So let's see, there's some coordinate axes. There's A1, B1, A2, B2. And then there's R. And I get to assume that AI is less than CI. So there's C1, there's C2, and DI is less than BI. There's D2, there's D1, so there's a rectangle Q. That is absolutely a rectangle, I don't care what you say. I claim that every point in Q is in the interior to R. So what do you need to do if you need to show that a point is interior to a set? You need to show that there exists a little number delta, so that as long as you think about a ball of that radius centered at that point, it's totally contained in big R. And, well, there's a point that's in Q. Well, let's even try to get an idea for how big a delta I could use. So the circle I draw had better not go farther south than that. It better not go farther east than that, west than that, or north than that. But if it's shorter than all of those line segments, then that whole ball is contained in R, right? So let's just decide how big that is. So this southerly line segment is shorter than C2 minus A1. This one is shorter, less than B2 minus D2. And the same thing for the east-west lines, but with ones instead of twos. So let's take this, well, I'm getting ahead of myself. So the delta I'm going to use is going to be the min of these four things. And each of those things has to be positive, right? So let's write that down. So let's let R be a rectangle, product of a bunch of AI BIs. Let's let Q be a product of a bunch of CI DIs. Let's assume that AI is less than CI and DI is less than BI for all I. And in fact, if you remember when, way back when in Calc 1, we stated the definition of an interval, CI is also assumed to be less than DI. So these inequalities hold for every I in 1 through n. Let's consider any P in Q. So there's the point P. So what we need to show is that there exists a delta greater than 0, such that the ball centered at P of radius delta is contained in R. Oh, well shoot, I'm out of time, so I'm going to write the delta to use, though you may have already done. And the proof will follow pretty easily from there. I'll take delta to be the min. Well, let's see, it needs to be less than all of the B minus D's. BI minus DI. And it needs to be less than all of the C minus A's. Where I runs from 1 to 1. No, you couldn't see that anyway. And I couldn't, if you just if you look at the picture, obviously that delta will walk. Now just, cool. So
I may wind up taking, well, it doesn't matter if the stuff is assigned today or Friday. I still due next week. Okay, so I won't bother tweaking the assignment yet. The most of the problems assigned today should be just fine. There's nothing about volume in it. It's just compute some interiors and compute some queries. Yeah, sorry I didn't have an extra one to give you.
Oh, turns out I just didn't have it in my folder. It was just like loose in my backpack, so I had the whole.
Happily, like this seems like an ideal use of the fact that I'm recording things.
Yeah.
If you want it.
Sure.